Hi, I am Peter Andras. I'm a professor at Edinburgh Napier University. This is my lecture series on the evolution of complex systems. This is lecture 3, the theoretical foundation, and this is part 2 of lecture 3. So, in this part, we will look at information subsystems, the concept of the double contingency, which leads to the emergence of systems, system identity, the identity violations, adaptations in the context of these systems, and finally, add the complexity of the systems. So, to remember what we said earlier, let's consider briefly again how we define complex systems. So in our context, these are communication systems. We have a number of communication units which generate the communications. And the system itself, it is the system composed of these communications. The communication units themselves are seen as abstract communication units where their key feature is that they can generate communication, they can receive communications, and they pass on these communications between them through some communication medium. However, these communication units are independent of the system, and we ignore what happens in them, and we focus purely on the fact that they can generate and receive these communications. So you have the sender unit, you have a receiver unit, and you have communications. The communications are generated as signals by the sender. These signals are transmitted and they are received. And we focus purely on this aspect of these communication units and on the communications in particular. We ignore what happens inside of the communication units because they are outside of the system. Of course, at the same time, we note that the communication units participate in many communications. Some of them are inside of the system and some of them may be outside of the system. And how they generate these communications impacts how they generate further communications. So in that way, they impact on the system, on the communications that are generated within the system. However, from the system's perspective, we focus purely on them as abstract communication units where we consider only their ability to generate and receive signals and to pass on these signals as a communication through some communication medium. So, earlier we discussed about the memory communications. And we said that memory communications are representations of past communications or patterns of communications that happened within the system. Now, let's consider how these communications are used, and how these communications are used and processed leads to the information communications within the system. Now, given that these memory communications represent past patterns of communications within the system, and given that patterns of communications within the system represent descriptions of the system and, in a complementary sense, descriptions of the environment, we can see these as information containing communications. They contain information about the system itself. Now, since we said that the system itself is about communicating about itself, these memory communications represent the information about the system and about its environment. So we consider information communications, those communications which reference memory communications and generate new memory communications. The information communications, in this sense, they process information and generate new information within the system. Now, by generating this processed information, is new information about what happened in the system and how the system is. The information communications increase the system's ability to reproduce and expand if they can increase the correctness of the description of the system's environment. So, for example, consider a company where they make minutes of committee meetings and decision making. Having this knowledge, having the information about what factors were considered when decisions were made, makes it easier to reference those conditions, makes it easier to generate new information within the organization by analyzing many of these decisions and using these to generate new decisions. If these new decisions improve the ability of the organization, let's say, understand their markets, then that organization will be able to sell more products, more services, and will be able to grow. Now, these information communications within the system may constitute an information subsystem if there are sufficiently many of them. There are sufficiently many references between these information communications, and they form a dense cluster within the system. So, for example, in the case of biological organisms, animals, the nervous system is a such information subsystem. Because the nervous system collects information about many things that happen within the organism, within the animal body. Collects this information and processes this information. And it uses this information to generate control actions for the muscles and various other body components of the animal. So the nervous system is actually collecting and processing information and generating new information about how the organism behaves. Similarly, as in the previous example I noted, the management within an organization produces the information subsystem within the organization. They analyze data, they make decisions, they analyze these decisions, they analyze them in the context of previous data and new data and so on. They generate new information communications within the organization, and in this way they generate the communications which lead to actions and behaviors of this organization, aiming to reproduce and grow the organization. Now, the information subsystem effectively describes a model of the system. So just remember that the memory communications are not necessarily equivalent of complete reproduction of earlier communication. They represent the information about these earlier communications and provide reference to the pattern. Combine these information communications, given that these are about information on the system, what the system is, and the complementary sense, what's the environment of the system. The information subsystem effectively describes through its communication a model of the system, or we may call it an identity model. So it defines what's the identity of the system in a summary form. Note that this is a subsystem of the system, so clearly not everything that's in the system is necessarily represented by this subsystem. So that's why we call it a model of the identity, a model of the system. It's not perfectly reproducing the system itself, but it is modeling, approximating the system and its identity. Now, where this leads is that information communications in general can be seen as identity definition, identity checking, and identity enforcement communications. So, for example, in the context of a company, these information communications generated by the management define what the company is, what the company does, what are the things that the company works on. They also defined identity checking communications, which check that communications, other communications that happen within the organization, comply with the identity of the organization. And there are also identity enforcement communications in case that some communications don't comply with the identity of the organization, then they enforce compliance. So, for example, the identity checking communications may check whether, for example, accounting reports are done properly, whether certain contracts or internal procedures are defined with in sufficient accordance with the identity of the organization. Identity enforcement communications will enforce this identity. So, for example, they may mean communications that instruct some members of the organizations to rewrite reports, or to interact with customers in ways to fix problems that were caused by earlier communications. Or among these communications, you can also see the communications which lead to the departure of some members of the organizations who don't fit through their communication behaviors into the organization. Or consider it, for example, the human psyche, the conscious self. This is constantly thinking about themselves, defining what is the identity of this particular human and what is not, how this identity fits with their behavior. Are they seen by others in the same way as they expect themselves to be seen, and so on? And what kind of corrective actions should be taken? Change of clothing, change of behavior, and so on. So these are examples of how information subsystems work in these systems, be them psychological, biological, or organizational systems. So now, having this concept of the information subsystem and the identity model of the system, let's consider again system perceptions and actions. So the system of communications, as we said, they change under the impact of the environment. So the communication units participate in various environmental communications that impacts on how they generate their communications, and that will have an impact on communications generated within the system as well, effectively on the compliance with the system referencing and continuation rules. Now, these changes, so the change in the patterns of communications that are generated within the system, are compared by the system to the expectations that are based on the model or on the identity of the system generated by the information subsystem. These are the identity checking communications within the system. And the effects of the environment are assessed in the interpretation context of this model of the system, or the identity of the system. It is checked to what extent the communications fit the expectation based on the identity. So if you remember earlier, we talked about the prior and posterior distributions. That this is a reconceptualization of the same thing. The identity of the system, or the model of the system represented by the information subsystem, determines what are the expectations, what are these priors effectively. And there is the evidence of the actual communications, and the question is, how do these match? Do they really match or not? Is there any need for correction or compliance imposition? So what you see here is that while previously we talked about distributions, and it was perhaps not obvious to how these distributions are operationalized, here this approach provides a much more operational interpretation. So there is a model, there is an identity of the system, which implies what is expected. And against that expectation, the actual communications can be compared and conclusions drawn, but to what extent these communications fit the system or the system's identity. Same way, if we look at the system actions, what you see is that the system generates communications, and those have an impact on the environment. However, these new communications that are generated by the system are communications which check its own identity, check whether the model of the system is correct given its environment. So these communications have an impact on the environment, and in general, the expected impact on the environment is that they help the reproduction of the system, help referencing further new communications from the environment, and help generation of new communications within the system through these references. So the system can be maintained and can be grown. So on one side, these communications are generated to check the validity of the system's identity. So they originate from system's identity. But then the expectation is that they will facilitate the interaction with the environment. So if you like, they describe the environment well, such that the system can reproduce and grow itself. So we provided now a revised interpretation of the action and perception of the system. We operationalized more how these perceptions and actions work using the concept of the system identity or system model maintained by the information subsystem. So, question is, what comes first? Is it the action or the perception? Because clearly, the system actions depend on the system identity. The system perceptions drive changes of the system identity. So on one side, the perceptions depend on the actions of the system, because the system generates these actions, they lead to perceptions. And then the actions also depend on the perceptions. So what actions are generated, they depend on the perceptions about the system's environment. So to give you a particular example, look at human development or animal development in the context of vertebrates in general. What you see there is that the fetus starts moving early on. These movements, to a good extent, are not fully clear of how this works, but what it appears to be the case is that the movements of the embryo generate perceptions in the embryo, in the fetus. And these perceptions, the ability to move and perceive what are the impacts of the movement on the body, lead to further perceptions and lead to further actions, and those lead to further perceptions. So through trying out how the body can move, the body learns how to move, and then tries out further moves and learns even more. So you get this kind of perception-action cycle where perceptions depend on actions and action depends on perception. Now, this double mutual dependence constitutes a double contingency. You have conditional probabilities of generating the next communications in a circular conditional arrangement. So on one side, the communications depend on the system model because they try to explore and track the validity of the system model. But the system model depends on the communications that are generated and are impacted by the environment to fit the model to this environment. So the question is how this double contingency, how this circular dependence of actions and perceptions within the system leads to the generation of a system. And what we see is that this double contingency, it is effectively the root of the system. How this works is that As the system emerges as a dense cluster of communications, where the dense cluster is there because these communications follow a certain set of referencing and continuation rules. As long as these rules are followed, there is a system, and effectively the system emerges when this dense cluster of communications is sufficiently separated from its environment, which is made of much less frequent, rarer communications. And the existence of this cluster, the existence of the system, gets questioned, where the system emerges from this contingency, where the communications within the system, questioning the validity of the rules of the system, lead to further communications and lead to further perceptions, and those lead to further actions. So, again, if you consider the human psyche, the human conscious self, questioning of oneself's own identity, who am I, is a key question. This is the root of this double contingency, because the answer to this depends on my definition of who am I. But by questioning this, I get further input from the environment, which validates or invalidates my assumptions about who am I. And in response to these, I revise to some extent, potentially, in some cases, the answer of the identity definition answer. So, questioning the existence of the perceived existence of this system is what leads to the further development of the system. Now, if a system has an information subsystem, and have to note that not necessarily all systems have a clear information subsystem. The information communications are there within the system, but they may not constitute a dense subsystem. However, if the system has this information subsystem, then it generates a new double contingency root for this information subsystem, and that helps the increased expansion of the system because the system can produce more communications, can produce better model of itself, can produce an identity that matches better the system's environment. So, for example, consider animals. In some simple animals, there are neurons, but there is no nervous system as such. So these are very simple animals. For example, consider sponges. They don't have exactly neurons, but they have neuron-like sensory system, sensory cells, which sense both outside of the sponge and sense what happens inside the sponge's body as well. And these neurons interact in a loose network and help the animal drive its behavior. It is a very simple animal, but it does not have a nervous system in the same way as other more complicated animals have. Most of the other animals, including the hydras and simple worms, they all have a much more organized nervous system. Now, the animals which have a nervous system generally are able to produce more complex behavior. So this more complex behavior, they can fit into a wider range of environments. and effectively they can reproduce more and they can maintain themselves more efficiently. So the animals with nervous system, which have their own information subsystem, perform in many sense better overall in a wide environment than animals without nervous system. However, it should be noted that animals without nervous system, such as sponges, have many environments where they can live perfectly well and can describe and adapt to their environment sufficiently well to maintain themselves and reproduce and expand. Now, we talked so far about the identity definition of the system, about information subsystem which defines this identity. Now, the systems experience identity violations. So these are when things happen within the system that do not fit the identity assumptions of the system. In a kind of wide sense, the identity definition of the system is given by the language of the system. If the system has an information subsystem, then it has an identity model against which the comparison of compliance with the identity of the system can be checked more explicitly and more quickly. So the first kind of identity violation are the faults. So these are communications that do not fit the language of the system. So as you know, as we discussed, the communication units can generate many kinds of communications. Some are within the system, some are not. If they generate communications meant to be in the system, but communications that do not fit the lexicon of the system, then these communications are faulty if they are meant to be within the system. Also, if some of the communications are not according to the rules of the grammar, so communications that have zero chance in terms of continuation probability, these are faulty communications. Another situation of identity violation is the error situation. So these are communications that follow the rules of the system, but it is impossible to generate a continuation for them according to the rules of the system. So in this case, the system's environment description is incorrect. The failure is a case when the system shrinks because there are so many error situations and faulty communications. So to give you examples, a faulty communication in the context of a company could be, for example, an accounting error, when the accountants type the wrong thing into the accounting report. It makes no sense, it can be checked, and it can be found quite easily, quite often, although not always. But it is something that should not be there. That's something that does not fit the rules of the communications within the company in terms of the accounting. An error situation, for example, is when the company follows its own rules about how to generate decisions, how to analyze data about customers, but they end up in a situation where there are products in the stores and they cannot sell these products. So they produce the products, but the products cannot sell. So the expectation in this case is that there will be further communications with customers which lead to the sale of these products. And these communications are not coming. So in a sense, what you see is that communications follow the rules, they generate the right products, store them in the right ways, get them ready for sale, and they cannot sell it. So the continuation communications are not happening. What this tells you is that the company's description of the environment is incorrect. Their expectation about their clients about what they want to buy are wrong. And the failure is when the companies make accounting errors, possibly intentionally, when they want to cover up something, when they want to embellish their financial performance. And they are also combined with errors when the expected growth is not actually happening, when the expected interactions with customers or with clients, other companies is not happening as expected. And this leads to failure when the company shrinks and potentially gets dissolved in the end. Now, in response to the identity violations, the systems adapt. The adaptation happens by changing the system. In a kind of general sense, this is a changing of the identity, or the changes might be quite minor elements in the identity. So changes can happen by changing the referencing and continuation rules, for example, by changing the structure constraints on continuation rules, changing the likelihood of certain communications. And these adaptations typically start by the information subsystem communications. So these are changes to the identity definition or the identity checking or the identity enforcement communications. Now, in general, the aim of these adaptations is to prevent the reoccurrence of the identity violations, be that faults or the sources of the errors. So going back to the previous example of the company, and the management communications within the company, if the company cannot sell the products that they produce, or that they follow all the rules and they expect to find the sales, customers who will buy these products, it's not happening. Now, what can the company do? Well, they can revise how they analyze their market data. They can revise how they analyze their customer survey data. What the customers want. They can revise how they produce their products. Maybe the products have some faults or some features that the customers don't like. So they can change how the company works. For example, by changing the product features, they redefine what is the identity of the company in terms of what kind of products are they producing. Or they may change how they analyze their marketing information, changing policies, changing rules about it. So in effect, they change their identity, possibly in relatively minor ways, but there are these changes. And these changes, these adaptations, are aimed to prevent the reoccurrence of previous faults. For example, if you consider the errors or mistakes in the accounting, a new management or new senior management may come in who may enforce much more strictly the honest reporting, the elimination of errors, and especially elimination of intentional errors in the financial reporting. Now, the adaptations, of course, they are not always the right adaptations. They may not increase the correctness of the system's environment description. Now, if they are wrong adaptations, then the frequency of faults and errors and failures will increase or may increase, and the system may actually shrink further. So, for example, again, take the company example further, they may change the product, they may add more features. However, those features may not meet the customer needs. So they made an adaptation, but it is the wrong kind of adaptation. And they keep shrinking further. So when the adaptations are made, they are made based on analyzing the information communications within the system and revising these. However, the analysis may lead to wrong adaptations as well, and that will lead to further shrinking of the system. All right. After discussing these theoretical concepts, let's finally consider what do we mean by the system's complexity. How complex are these systems? Look at the examples. You see here three pictures. One is a bacterium, a cell, another is an organism, and then you have humans, a um, social organization of humans. Now, clearly, these all are complex systems in a kind of everyday sense. The cells produce complex behavior. They have millions of molecules in them. It's very complex. The animal, even as a simple medusa or a jellyfish, it still has tens of different cell types, potentially hundreds of thousands, millions of cells, which produce very complex interactions between them. And human social organization, well, they produce many interactions, many complex behaviors. So clearly, these are all quite complex systems. But the question is how to measure the complexity of these systems. Now, one way is that you can consider a description of the system in some language. And you can measure how long is a description of the system in this language. So, for example, consider a watch. Now, typical watches are considered, mechanical watches are considered quite complex. And indeed, if you ever took apart a watch, a mechanical watch, you would see that there are really, really many components. The number of components is typically in the hundreds, if not the thousands. So it is a complex mechanical system. But look at the human body. Well, I mean, so far we don't have a full description of it. Just to know that, for example, in the retina, which is a small part of the human body, it is the patch in the eye which senses incoming light. Yeah, more or less every year there is a new cell type that is discovered in the retina. So we are very far from providing a proper description of what's in the human body. Of course, there are many descriptions, many approximative descriptions. Or take computer programs. Now, clearly, computer programs are written in a computer programming language. So you can take that language and use the program description in that language, and that is the description of the program. So what you see is that you can have descriptions of various systems. Some you can describe exhaustively, like a watch or the computer program, while in some cases, like in the case of the human body, you have all kinds of approximative descriptions. So, how should we use these descriptions to measure system complexity? Well, you can use the system's own language if you know that to describe. Of course, quite often we do not know the system's own language. So how long is the system's own description? Or, alternatively, you can use super equivalent language, something that can describe everything that can be described in the other language. And then you describe the system in that, and you measure the length of the description there. Now, the advantage of the second approach is that if you have this super equivalent language, which can describe anything that has a language that is sub-equivalent to this, then you can use this language to compare complexities. So, for example, in the case of computer program, you can use its own language, the programming language that was used to describe it. In the case of the cell, you don't know the cell's own language. I mean, we know quite a lot about it. We know that there are all these molecules. We know to the extent where some of the molecules are, how they interact, and so on. But we are still unfortunately quite far from knowing the full details of what happens in a cell, even in very simple cells such as bacteria. Now, we mentioned superequivalent languages. So in general, two languages are considered equivalent if they can describe objects of equal complexity by equal length descriptions in general. Of course, there might be some exceptions, but in general, for the majority of objects that can be described and which have the same complexity, you get different equal length descriptions. A language is super equivalent compared to another one. It can describe the same object, the same detail in a shorter description. Now, to give you some example here, if you come across fractals, there is typically most of these fractals, which are very nice complex pictures with many fine details. They look very complex. However, typically you have a relatively simple mathematical formula that is used to generate these very complex images. So for example, if you came across the Julia set or the Mandelbrot set, these are fractals which look very, very complicated. However, they are relatively simple mathematical descriptions which define how to generate these sets. So on one side, if you take the language of graphical description, the picture representation of these sets, you get a very long description which will never be fully precise because there are details that are not visible at the resolution that you use. While at the same time, you can use a mathematical language, which in this case it's a super equivalent language compared to the pictorial language, in which you can write possibly about 5-10 lines of description, and that description defines exactly the same object with a much shorter description. Now, in general, you pick a language and you provide an approximate description of the system in that language, which is an approximate description to up to some detail of the system. And then you measure the length of this description. That gives you an approximate, an approximation of the complexity of the system. Of course, it's a question of how close is your approximation. How much of the system behavior is not described by the approximate description. You need to consider that. However, this gives you an approximate complexity combined with an assessment of how good is your approximation as well. So that on one side you have an approximate complexity measure plus an approximation of the mismatch between your approximation and the reality of the system. These two together will give you an approximation of the complexity of the system. Now, by definition, the environment is seen as infinitely complex because it has so many communications of all kinds. So we define it as an infinitely complex environment. Now, clearly, if it could be described completely, then it would become part of the system, and it's not. So there is environment always outside of the system, and this environment is infinitely complex. Now, the system exists in this infinitely complex environment. How it exists? It describes itself and describes an approximation of its environment. Now, the system survives or reproduces, maintains itself if the description of its environment or of itself captures sufficiently the environment to generate appropriate actions to maintain and expand itself. So, as long as the system produces a sufficiently good approximation of its approximate description of its own environment, then the system can maintain and reproduce itself in its environment. So, for example, consider cells or organisms living in an environment. They fit their environment, they adapt to the environment, and they are able to describe this environment for themselves sufficiently well that they are able to pick nutrients, resources from this environment such that they can maintain themselves, they can generate new molecules, molecular interactions, and they can maintain themselves as communication systems within their environment. So, what we say in this context about the complexity of the system is that the environment is infinitely complex, and the systems which survive, which reproduce and maintain themselves in this infinitely complex environment, must have sufficiently close approximations of this environment, which approximations must be very complex, given that the environment itself is infinitely complex. So, an alternative way to look at the complexity of the system is to look at the environment where it can survive, and the complexity of the system will be reflected by the complexity of this part of the environment where it can fit in and survive in an adapted way, in a complementary sense in this environment. So, to summarize, first we looked at information communications and the information subsystem. We said that information communications are the communications which reference memory communications, generate new memory communications, new representations of the information about the system. And when these information communications are sufficiently many and form a dense subcluster of communications within the system, then the system has an information subsystem. Having an information subsystem benefits the system because it allows the system to define a model or an identity for the system, and that can be used to check the validity of communications within the system to a better extent than without the information subsystem. And that means that the system can adapt better to its own environment. We discussed about system identity, which is defined by the information subsystem, which is effectively a model of the system, and how the system identity works by identity definition, identity checking, and identity enforcement communications. Then we discussed about identity violations, about faulty communications, about error situations, and failures. The faulty communications are the communications that do not fit the lexicon of the system or do not fit the continuation rules of the system. The error situations are the situations where the system follows its own rules but cannot generate continuation communications. And the failures are when there are many errors and faults, and as a result, the system is shrinking and potentially it gets dissolved at the end. Now, in response to these identity violations, the systems adapt, and they adapt by adapting their identity, by their definition, the identity checking communications, or then identity enforcement. Now, in general, the expectation is that these identity adaptations are useful and they improve the system match with its environment. However, we also noted that not all these adaptations are useful, and sometimes the system generates wrong adaptations, which actually do not reduce the frequency of faults and failures and errors, and potentially may even increase these, and then the system is actually continuing its trajectory towards dissolution. Then we discussed about the interpretation of actions and perceptions in the context of systems with an identity model and an information subsystem. And we saw how the system checks its perceptions and generates actions to validate its own identity. So checks perceptions against identity and generates actions over the environment to check its own identity, to validate its own identity. Now, this interdependent cycle of action and perception generation, this circular contingency, constitutes a double contingency which effectively induces the emergence of systems. Now, the double contingency comes from questioning the existence of the system when there is a dense cluster of communications which follow a particular set of continuation and referencing rules, then the existence of these systems can be questioned. By questioning the existence of the system becomes a system. And as long as the system can question its own existence, its own identity, the system does exist and generates new communications maintaining the system itself. Finally, we discussed about complexity of the system, discussed about how the description of the systems in some language can give you the information about the complexity of the system. We noted the environment is infinitely complex, and that any system which survives in such infinitely complex environment must be a very complex system. And we discussed about how these various languages can be used and how approximate complexities can be used to assess the complexity of systems in combination with some assessment of the part of the system that is not described by the approximate description. All right, so let's have a look at a few questions and answers. Is it true that the nervous system is a special subsystem of the organism dealing with information processing within the organism? Well, yes, this is what we said in our examples. The nervous system is really made of neurons, which deal with both the perception of what is happening within the organism and also with the generation of actions, the control of actions that the organism generates to interact with its environment. So indeed, the nervous system, it is the information subsystem of animals. Next question. Give an example and explain the concept of double contingency. Well, we did discuss how this double contingency works. We said that if there is a system in emergence, in the sense that there are rules of communications, continuation and referencing rules that are followed, then the existence, the identity of the system can be questioned. And when this happens, that's when the system is effectively emerging. Now, to give you an example of this, we consider, for example, the science of mathematical biology. Now, mathematical biology came around well, about perhaps 60, 70 years ago. Effectively at the interface of mathematics and biology. On one side, there were mathematicians who would try to describe models of biological things, cells, organisms, biological behaviors. On the other side, there were biologists who were looking for mathematical formulae, mathematical concepts that can be used to describe biological phenomena. At the interaction of this group of scientists, what happens is that they wrote papers which will be published at the beginning in various biological or mathematical journals without being specialized in mathematical biology as such. But these papers reference each other. And as many of these references emerge and a community of scientists emerges, coming both from the biological and mathematical end, who start to speak a common language which is combining biology and mathematical concepts. This is how the subsystem of science, the mathematical biology, emerges. So there are many communications referencing each other. There are individuals, scientists, who communicate with each other by letters, emails, and so on. At that time, there were no emails, of course, but there were letters. And these communications raise the question of, is there a scientific community of mathematical biology? Is there a subfield of science of mathematical biology? And when that question arises, because they see that they follow the same continuation and referencing rules, if you like, in their scientific communication, when this question is formulated whether there is a subfield of mathematical biology, that's when the subfield of mathematical biology becomes into existence. And then they establish dedicated journals, dedicated conferences. They become selective. They decide what really belongs there and what doesn't. They establish the rules of how they check what belongs there. And you have a new emerging science subsystem. Next question. Can we measure the complexity of an engine by listing all the components in it? And how could we add to this complex measurement the impact of the interdependencies between the listed components? And well, the answer is yes, you can measure the complexity of the engine. Typical engines have perhaps a few tens, maybe a couple of hundreds of components if you dismantle it and place them one after each other. And of course, in order to really capture the complexity of the engine, you should also describe which parts interact with which other part and how. And of course, you can list these interactions as well. You can list which screws go where to keep parts together, which parts do what, for example, maintaining small explosions, moving as a result of the explosions, and so on. Which are the parts that move together, and so on. So you can describe all these interactions, and describing the interdependencies between the components actually gives you a much fuller measure, a much fuller estimate of the complexity of the engine. Next question. Can a system have higher complexity than its environment? And the answer is no. As we said, the environment is infinitely complex, much more complex than any system that exists in that environment. So the environment complexity is always higher than the system's complexity. This also shows you, for example, if we apply this to the information subsystem of a system, the information subsystem is a subsystem of the system. So as a result, the model of the system, the identity of the system that is produced, the identity description that is produced by the information subsystem will always be only an approximation of the actual full system. So that's why we use the terminology of the model, because it is a model. It's not fully representing the full system. There are parts of the full system that go beyond of that model. The question is how good that model is. Finally, consider MS Word text editor software. How could you measure the complexity of this software system? Well, in this case, the answer, there is a relatively straightforward answer, which is that you take the code of this text editor. Now, clearly this text editor is a big piece of software. Most likely you have there about millions of lines of code. However, you can actually take the code of all components that in the Microsoft Word are used, put them together, and then you get an actual description of this software, and the length of this description will give you a measure of the complexity of this software. Thank you.